Thank you so much for inviting me for this talk, and thank you so much for being so numerous today. I have a lot of things to talk about, but what's interesting in my mind is that these things are linked together in a really interesting way. At least that's what I'll try to convince you about. So the title talks about System 2 cognition, which is about high-level cognition. And that's connected to consciousness, as I'll explain. It's also connected to issues that are very important today in machine learning about generalization out of distribution. And it's also connected to the notion of agency and reinforcement learning and how agents face problems that standard static machine learning hasn't been looking at enough already. So deep learning has made amazing progress in the last few years and decades. And some people think that it might be enough to take what we have and just grow the size of the data sets, the model sizes, computer speed, just get a bigger brain. But I'm not quite of this opinion. I think that we're missing out in qualitative ways in order to approach human-level AI. We have currently machines that learn in a very narrow way. They need much more data to learn a new task than our human examples of intelligence. They need humans to provide high-level concepts through labels, and they still make really stupid mistakes. They're not very robust to changes in distribution. They're adversarial examples and things like this. And so some people, contrary to the first ones that I mentioned, think that we have to start afresh and invent something completely new to face these challenges, and maybe go back to classical AI to deal with things like high-level cognition. What I'll try to tell you about today is that I think there's a path to go from where we are now, expanding the abilities of deep learning, to approach these kinds of high-level cognition questions of System 2. So I talked about these two things, System 1, System 2. Let me try to be a bit more precise. I really got introduced to these concepts by reading the amazing book of Daniel Kahneman, which I suggest you to look at, Thinking Fast and Slow. And he talks about these two kinds of cognitive tasks. System 1 are the kinds of things that we do intuitively, unconsciously, that we can't explain verbally, and that we can, in a case of behavior, that are habitual. This is what current deep learning is good at. So if you're driving a car and going back home to a place you know, you don't need to pay a lot of attention to the road. You can talk to the person near you. On the other hand, if you're in a new city and you don't know the way, maybe somebody told you directions, but you have to really pay attention to every corner. You have to read signs, you have to be on the lookout, and if somebody tries talking to you, you will ask them to, please let me drive. So what's going on there is that you're generalizing in a more powerful way, and you're doing it in a conscious way that potentially you could explain. So if I ask you to add 34 and 56, you can do it in your head, but it's going to be sequential and slow compared to a calculator. The kinds of things that we do with System 2 include programming. So we come up with algorithms, recipes, we can plan, we can reason, we can use logic. Usually these things are very slow if you compare to what, for some of these problems, computers could do. And these are the things that I'm going to argue that we want future deep learning to do as well. So here are some things that I think we're missing in order to approach human-level AI with deep learning. We need to work better on out-of-distribution generalization and transfer. So when you learn a new task, you want to be able to do it with very little data. We want to be able to handle these high-level cognitive tasks that I mentioned, including using these tasks to force the learner to discover the kind of high-level representations which deep learning was supposed to be about in the first place. Deep learning was about learning multiple levels of representation, with the highest level supposedly corresponding to the kind of concepts we manipulate with language. And many of these concepts have to do with causality. The kinds of concepts we manipulate with words tend to be cause or effect. And once you start talking about causality, you have to also talk about the agent perspective, something that the mainstream of machine learning hasn't paid enough attention to. Not just because we want to solve reinforcement learning problems, but because we want to have machines that understand the world, that build good world models, that understand cause and effect, and that can act in the world in order to acquire knowledge. So a big theme of my presentation today is that these different questions are not independent research directions. They're connected. When you make progress on one, you can make progress on the other, and understanding how they are linked can help us plan a path for our research. So let me talk a little bit about consciousness and the kind of functionalities that I think we need to add to machine learning. So this is the roadmap for this talk. I'm going to start by talking about the need for having machine learning systems that can handle changes in distribution, and why it's particularly important for agents because of non-stationarities in their environment. Then I'm going to talk about the building blocks that I think can help us get there. In the last few years, maybe unnoticed, we have added things to the deep learning toolbox, in particular attention mechanisms, which I think are actually the key to move to the next stage that I'm talking about. And in this part of the talk, I'll also tell you a little bit about how much work has been done by our colleagues in cognitive neuroscience to better understand the human side of the equation. Then I'll talk about several priors that may be linked to consciousness. So the main theme here is that there's an advantage for human beings to have these high-level cognitive abilities. And so these advantages, you can think of them as assumptions about the world. So usually we talk about priors, or you can think of them as regularization. So the first one that I'll talk about is the idea that the joint distribution between the high-level concepts can be represented by a sparse factor graph. Any joint distribution can be represented by a factor graph, but the sparse one is a different story. And then I'll talk about another prior that has to do with how the world changes. And this is going to connect with the notion of agency. So the fact that most of the time when things change in the world, it's because agents, like people, do something. So we intervene, we do things, and the hypothesis that I'm proposing with other people is to consider those changes as localized in some abstract space. And if we use these hypotheses, I'm going to show through some of the recent work we've done, you can actually discover relationships that are just causal relationships between variables. Yeah, I'm going to also talk about meta-learning, which is connected to the problem of learning out of distribution. And the final bit of my presentation is going to be more about the detailed architectural structures that we should explore to introduce the kind of compositionality that System 2 processing requires. And in particular, I think we should be moving towards neural nets that can not just operate on vectors, but also operate on sets of elements, sets of vectors, sets of objects that are pointable, that can be referred and operated on by dynamically recombined modules. So that's it. That's the end of my talk. This is the talk, right? Now, I'm going to go a little bit more detail on each of these points. Let's start with changes in distribution. So the classical framework for machine learning is based on the hypothesis of IID, independently and identically distributed data. That means the test data has the same distribution as the training data. And it's very important because if we didn't have that assumption, then we would not be able to say anything about generalization. Why would a function learned on some data work on some other data, right? Now, unfortunately, this assumption is too strong. And reality is not like this. Most of the data we get isn't IID. And so in practice, what many people do in industry or in academia is when they collect data, they shuffle it. And here, to make it IID. And here I want to quote my friend Leon Boutou, who in his ICML keynote this year said something like, nature does not shuffle data, we shouldn't. And the reason why we shouldn't is because when we do that, we destroy important information about those changes in distribution that are inherent in the data we collect. And instead of destroying that information, we should use it in order to learn how the world changes. So this is important because there are, for example, rare events like black swan events that are highly unlikely to happen but could have severe consequences. And this question of out-of-distribution generalization really breaks the IID hypothesis. Now, the IID hypothesis was good, but if we discard it, we need to replace it by something else. And that's why I've been talking about priors, and one of the important ones is gonna be, well, how is the test distribution gonna be related to our training distribution, if it's not the same? Okay, so let's talk about out-of-distribution generalization. What I mean by out-of-distribution generalization is essentially the phenomenon of learner being able to generalize in some way to a different distribution. It doesn't say anything about how we do it. But let's see why we need this. Well, if you are a learning agent, so agent means actions, right? So it's a learning system that's embedded in some environment. You're almost always facing non-stationarities for several reasons, right? There are changes in distribution due to the actions of the agents. I move to a different place. The actions of other agents, the fact that I'm moving, that we're looking at different times, different sensory signals, different sensors, different actuators, different goals, different policies, all kinds of things are changing. And as you heard from Blaise talk this morning, once we start looking at multi-agent systems, it gets even more complicated. You can't even talk about optimization as he was explaining, but certainly from the point of view of each agent, you don't have a stationary distribution anymore. And if you think about a child learning, for example, their world is changing all the time, their body is changing all the time. And so we need systems that are going to be able to handle those changes and do things like continual learning, lifelong learning, and so on. This has been a long-standing goal for machine learning, but I think we haven't yet built the solutions to this. And one of the crucial elements, according to me, in order to be successful in this, and I'll come back at the end of this presentation much more on this, is introducing more forms of compositionality. So what does that mean? It means being able to learn from some finite set of combinations about a much larger set of combinations. We already get that from distributed representations. Distributed representations are really at the heart of why neural nets are working. They were introduced by Jeff Hinton in the early 80s. And in the last few years, we actually have theory that helps us see why you get an exponential advantage, potentially at least, if you make the right assumptions, if we're making the right assumptions about the world in terms of compositionality, in terms of being explained by a number of different variables and factors, then the distributed representations can be exponentially advantageous, because essentially, once you've trained a bunch of features, you can generalize to new combinations of those features. This is what a single hidden layer already gives you. Now, if you have a deeper network, you also get compositionality, because each layer gets composed with the next one. And we've also shown that gives another exponential advantage. And now, I think there are other forms of compositionality, and the one that we know best is the one you find in language. And linguists have been talking about this for a long time. They call it systematicity or systematic generalization, and I'll talk a lot more about that. So this opens the door to better powers of analogy, of abstract reasoning, and that remains to be done in machine learning, I think. So systematic generalization really is aiming at out-of-distribution generalization and fast transfer, but it's about how we do it. It's about the idea that we can get that by dynamically recombining existing concepts. So it could be in language, but it could be in other settings. Like in the picture here from Lake et al. 2015, we invent a new type of vehicle by combining properties of different vehicles. But what's interesting about this is dynamic systematic generalization allows potentially to generalize to combinations that have zero probability under the training distribution. It's not just that they're not present in the training data, they would have zero probability under the training distribution. So as an example, if I tell you a science fiction scenario, clearly you haven't lived something like this in your life, but you can still imagine it. If you've been living all your life in some continent or some city, and then you move to a completely different place, and you have to drive in this unknown city, as the example I gave earlier, you are also doing a form of systematic generalization. Unfortunately, current neural net architectures are not that good at doing that, and it's been shown through several papers and experiments, starting in particular with the work of Lake and Baroni, more recently the work we did at Mila, led by Badano and collaborators, presented by Eggclear. Currently, we have a paper that's going to be on archive probably tomorrow or the day after on Clever, which is a data set for visual question answering, where there are combinations of the linguistic concepts that are present in the questions that just don't come up in the way that the data is generated. And the current methods, when you ask them to answer these kinds of questions, fail completely, whereas the human we wouldn't even realize that these combinations are not present in the data. Okay, and then one question people may come up with is how what you're proposing is different from the classical AI program of symbolic logic and so on. So that's a good question. Well, I think there are a number of reasons why these classical AI programs had trouble. And in the work that we need to do in order to achieve System 2 performance, we want to avoid some of these pitfalls. We want to make sure that those systems will be able to generalize efficiently in a large scale. The concepts that we want to learn need to be grounded in with System 1 in low-level perception and action. We want to keep the power of generalization of the distributed representations. We want to make sure that the kind of search that is involved in things like reasoning and planning can be done efficiently, whereas the classical approaches require a huge number of explorations of many trajectories of how things could unfold or how you could combine concepts, rules, and so on. And finally, we need to make sure we build systems that can properly handle uncertainty in the world, and machine learning has been doing a pretty good job at that up to now. But we want to achieve these extra goals that we're not doing very well at, like systematic generalization that I explained, factorizing the knowledge, or at least some of it, that the learner is acquiring in small exchangeable pieces to get this combinatorial advantage that I've been talking about. And that includes being able to manipulate variables, things that you do naturally in programming and in logic formulations, dealing with instances that are associated with more general categories, if you want, and having references and indirection, things that don't seem natural in the neural net world. But as I'll try to convince you, we now have actually built the tools for doing that in deep learning using attention mechanisms. Okay, so let's talk about attention and consciousness. So what is attention? Attention is about doing computation in a focused way. We're going to sequentially focus computation on one or a few elements at a time. And we realized in around 2014 that this was extremely powerful and was the reason why we were able to get a breakthrough in machine translation. When you produce the next word in English, when you're trying to translate from French, say, you want to really focus the computation on just the right few words in the French sentence that are relevant to do the translation. So we introduced a particular form of attention called content-based soft attention, which is very convenient because you can backprop through it, and so you can learn it. In other words, we can learn where to attend. And so the way it works is the computation being done at the next level is going to use as input a selection from the previous level of computation, and that selection is going to be a soft selection. So we can take a convex weighted combination of value vectors from the previous level, and these convex weights are coming through a softmax that is conditioned on each of the elements. So for each of the elements, we're going to see how well they match the context to see on which one the attention should be focused. So in a way, attention is parallel, right? We're considering all the possible elements in some set, and we're computing a score for each of them in order to decide on which one or which ones we're going to put attention. And there's been recent work in cognitive neuroscience showing that attention should be thought of as an internal action, right? So the way that your brain is attending is very similar to the way that your motor system is deciding to move your arm. And so we want to learn these attention policies. So attention has been very, very useful. I mentioned machine translation, but essentially today's NLP systems, state-of-the-art systems, all rely on attention. Look at all the work based on transformers and their variations. They're also at the heart of memory extended neural nets. We had a paper last year and more ongoing work on how attention connected to memory can also unlock the problem of vanishing gradients. And as I'll mention, attention also allows to change neural nets from machines that are processing vectors to machines that are processing sets, and in particular sets of key value pairs. Okay, so let's see this picture again. We can think of attention as creating a dynamic connection between two layers, whereas in a traditional setting, the connections are fixed. Here, we kind of pick which of the inputs is going to be sent to the whatever module we're considering that uses an attention mechanism. Now, this is great, but from the point of view of the receiving module, there is a problem. It gets this value, which is one of those in the set of input elements, but it doesn't know where it's coming from, right? It's the value of what? And so what we're doing with attention mechanisms is, in addition to the value, we have some concept of key. In other words, a kind of identifier for where the value is coming from. Currently, we're using those keys to decide which element should get the attention. But that key is also sent to the next level, and so downstream computation can know what the value it's getting is what it is, what it's coming from. What kind of object it is, what kind of type it is. So you can think of this as creating a name for these objects and creating a form of indirection. And as I said, now we have these systems of operating on sets. Why is it a set? Because the attention mechanism doesn't care of the order in which we're putting these elements in the first layer. It just picks one according to how well it matches some kind of learned policy, but the information about the relative position of these elements in say in your brain or in a neural net architecture doesn't matter anymore. Okay, now let's connect to what our friends in neuroscience and cognitive science are doing. In our community, the C word, consciousness, is still kind of taboo, but in their community it's not anymore, and that's great. They've made a lot of progress in understanding several aspects of consciousness, and there are a number of theories, but many of them are related to what's called the global workspace theory, which originated from bars, and there's a lot of very good, important improvements to it from Stan Dehan and collaborators. And what this theory says is that what's going on with consciousness is there's a bottleneck of information. Some elements of what is computed in your brain gets selected and then broadcast to the rest of the brain and influencing the rest of the brain. So this is related to short-term memory, where the things that have been selected are available and conditions heavily perception and action. So it also gives rise naturally to the kind of system 2 abilities that I've been talking about. All right, so how is machine learning going to do something? I mean, what's the connection with machine learning? Machine learning could be used to help brain scientists better understand consciousness, but what we are understanding of consciousness could also help machine learning develop better abilities. So first of all, the work that's been done in neuroscience in general is based on fairly qualitative descriptions of these functionalities that we think are associated with consciousness. And what machine learning can do is help us formalize in a way that's more mechanistic what these exactly means. And then that could feed back the research in neuroscience in order to provide more specific tests that could be done of these theories. Of course, for me at least, one of the motivations is also to get rid of the sort of fuzziness and magic that surrounds the word consciousness. And I think machine learning is in a good position to provide a justification for these particular forms of computations, in the sense of why have they evolved? What kind of computational and statistical advantage are coming with these particular forms of computations? And of course, once we understand these things, we also want them in our learning agents. So consciousness is closely related to language, because the way that we know that somebody is conscious is by asking them to report what they're thinking about. So this is the direct way that we know about consciousness, and that means that there's a very strong link between your thoughts, things that you're conscious of, and language, that one can be translated to the other fairly easily, although there's a loss of information when you go from your thoughts to language. It also means that there's a connection between system 1 and system 2 here, because those high-level concepts that we communicate with language are anchored in the system 1 sort of intuitive system that connects your brain to the rest of the world through perception and action. And I think that's one of the big important direction for natural language research. We really want to explore things like grounded language learning, where we don't just learn from texts, we learn from environments which involve perception, action, the perception-action loop through the environment, and allow a learner not just to get sort of patterns of sequence of words, but also what they refer to is as its understanding, potentially implicit, of how the world works. And I refer you here to some work we've done recently and published at the last iClear on grounded language learning, something that I called Baby AI. Okay, so now we're at the part of my presentation when I'm going to talk about the kinds of priors, the kind of structures, the kind of assumptions and regularization that we could use in order to encourage our learning systems to do a good job at out-of-distribution generalization and the kind of conscious processing abilities that I've been talking about. And the first one I want to talk about is the sparse factor graph assumption I mentioned. I called that in a 2017 paper the consciousness prior. So in this paper, I talk about the way that cognitive neuroscience has been understanding conscious processing, the fact that we form these low-dimensional conscious thoughts that are obtained by selecting elements from a larger unconscious state, right? So now instead of having a single top-level representation like we usually have in our systems, we have two. There's a very high-dimensional unconscious state which contains all of the things you could think about, and then there's a tiny, tiny one which only contains those that went through the bottleneck recently. That's the conscious state. And then attention, of course, is used to select from the first one what goes in the second one. And attention is also used in a top-down way to condition further processing in the system 1's computation. So now that way of thinking about conscious processing is about the sort of computation we're doing, but in machine learning, we're also used to think about what do these computations mean? And often they mean some kind of inference with respect to some model of the world, which might be implicit. And a good way to think about a model of the world includes what kind of joint distribution between the high-level concepts are we talking about? And so the consciousness prior proposes that it's a sparse factor graph. So a factor graph is just a particular representation of joint distributions. You can represent any joint distribution in this way. It has these squares that correspond to factors that are kind of relations between variables. The nodes are other variables. And sparsity here just has to do with how many neighbors each node has. So why do I think that it's a good hypothesis? Well, think about the kind of statements we can make with natural language. Like when I say, if I drop the ball, it will fall on the ground. Now, this is a very powerful statement because it's true with high probability, and yet it involves very few variables, just the words that are there. So the fact that it uses very few words means that the relationships that are being described can tightly capture some element of the joint probability through very few variables at a time. So you can think of like each of these black squares, each factor corresponding to the relationship between a small set of variables of the kind you could produce with natural language. Now, this is different from the usual assumption that you find in many papers these days that study high-level representations that are supposed to be, where the variables are supposed to be independent of each other. This so-called disentangling work, which I think is a misunderstanding of the goals of deep learning, which was to learn these high-level representations. And so instead of thinking of these variables as completely independent at the top level, we think of them as having this very, very structured joint distribution. And they have to be like this because high-level concepts like, say, ball and hen that I just used are not independent. They come in these very powerful and strong relationships, as I showed. So then what I'm saying is, instead of imposing the very strong prior of complete marginal independence at the high level, we can have this slightly weaker prior, but still very strong prior, that the joint is represented by a sparse factor graph. The reason I say it's still very strong is that this prior, for example, would not work in the space of pixels. You can't find easily a small group of 5 pixels in images such that you can predict one of the pixels with high accuracy given the 4 others. But we can do that with natural language when we express those statements at this high level. So factor graphs are expressed by writing the joint as a product of these partition functions like the phi k here, where each of these partition functions involves only a few subsets of the variables. And so what it means if we were to impose something like this is it puts pressure on the encoder, say, that maps the low-level data to the high-level representations to have that property that the factor graph is sparse. Okay. So next, I want to talk about the meta-learning aspect and another hypothesis that's important to deal with how the world changes. So meta-learning is something really hot and cool these days, but actually started several decades ago. My brother and I have been working on this in the early 90s and actually was Sami's PhD subject. And what it's about really is about having multiple timescales of learning or multiple timescales of iterative optimization like computation. So typically you would have an inner loop like normal learning and an outer loop like evolution, which optimizes whatever the inner loop is producing. And so in this way we can talk about the evolution outer loop with individual learning inner loop, or we can talk about in the life of an individual lifetime learning as the outer loop and individual adaptation to a new environment as the fast time scale. And the thing that's cool about meta-learning is it allows us to explicitly optimize for generalization. And in particular, it can be used to explicitly optimize for out-of-distribution generalization, right? If the agent sees multiple environments, we can train its slow timescale metaparameters so that it will generalize well to new environments. Now, there's the question of that I mentioned earlier, what kind of hypothesis can we make about these changes in distribution? And because underlying physics means that typically an action by an agent is going to be localized in space and time, we can assume that the changes in distribution correspond to or are caused by or the consequence of an intervention by an agent that acts on just a few causes or a few mechanisms that relate variables with each other. So this extends a hypothesis that was proposed by Shopkoff and collaborators of independent mechanisms. And what they mean here is informationally independent, meaning that the the relationships between variables, the mechanisms, the conditional distributions are independent in the sense that what you learn from one doesn't tell you anything about another one. And so if something changes in the world, one of these mechanisms changes, one of the conditional distributions corresponding to, say, one of the nodes in this graph, it's like a graphical model, for example, if something like this changes due to an intervention, you only need to adapt the part of the model that corresponds to the change. So, for example, if I put on some sunglasses, the data that I'm getting at on my retina is very, very different. But it can be explained by a tiny change, which is this one variable that changes its value from 0 to 1. So that's really interesting, because if we have such hypothesis and we have a good representations of the interactions between all those high-level variables, then very few bits would be needed to account for those changes, and thus very few observations needed to adapt or infer what has happened, and thus we can get good out-of-distribution generalization. So, so the idea is, since out-of-distribution generalization can be obtained if we have the right decomposition of knowledge, we can use out-of-distribution performance as a training signal for factorizing knowledge. Okay. So we did some work in that direction. There's a paper called the Meta-Transfer Objective for Learning to Disentangle Causal Mechanisms, where we applied this idea in very simple settings where you have just two variables, A and B, or say 4 variables, A, B, X, Y, and A is the cause of B, but the learner doesn't know, and you might observe just X and Y, which are simple like rotations of A and B. And it turns out that if you have the right decomposition, if you look at the right way of factorizing the joint distribution between A and B, the one in which we have P of A, the cause, multiplied by P of B given A for the effect given the cause, then when there's a change in distribution due to an intervention on the cause, the learner that has the right model will adapt much faster, doesn't need as much data. So the x-axis on this thing is the amount of data that the learner needs to recover from a change in P of A. And it turns out that you can also use this to learn about how to map the XY, which is things like the pixels that don't have a causal structure, to the A's and B's that are the high-level variables that have causal structure. Because, again, the same remark as I did earlier with the consciousness prior, which does not apply on the pixel level, the assumption that these high-level variables are causal does not work on things like pixels. You can't really find a pixel that's a cause of another pixel, right? So it's not the right space for doing things. We had a more recent paper called Learning Neural Causal Models from Unknown Interventions, where we extend these ideas to larger graphs in such a way that we can avoid the exponential explosion of the number of graphs that need to be considered by parameterizing in a factorized way the distribution over graphs. And one of the things we find is that in order to really facilitate the learning of the causal structure, the learner should try to infer what was the intervention, on which variable was the change performed. And that's something we do all the time. Like most of the time, at least my brain is trying to figure out what was the cause of what I've observed or that explained the change that I'm seeing. So we tested these ideas on various small graphs, and we were able to find that actually this works quite well and better than the commonly used causal induction methods. But more importantly, the way that we're attacking this problem is something that's very deep learning friendly, in the sense that we just define an overall objective, some regularization terms, the usual things, and we do gradient descent on it. Okay, the last bit of my presentation is about operating on sets of objects that may be pointable using dynamically recombined modules, which I promised at the beginning. And so we have another recent paper called RIMS for Recurrent Independent Mechanisms. And it's about modularizing the computation and operating on these sets of named and typed objects, but in a deep learning way, as you'll see. So we apply this idea to recurrent nets. The state of the recurrent net is broken into pieces. Let me see if this works. All right. So each of these boxes represent a small recurrent net that is updated based on its previous state, but it can also be updated based on the state of other subnetworks. But we are constraining the way that these subnetworks are talking to each other so that it's going to be sparse and it's going to be done in a dynamic way. So what it means is that using attention mechanisms, the connectivity pattern between those modules is changed and computed on the fly. Also, we use the attention mechanisms to select a subset of the modules that are going to be activated. So this is the idea that there's a bottleneck that dominates the computation. And the other important element is that the things that are communicated between those subnetworks are not the usual standard vectors that we use in recurrent nets. They are these sets of key value pairs. And so what it means is that what these networks are exchanging is, you can think of them as variables along with something like their type. And what we found is that this leads to better out-of-distribution generalization than standard methods that don't use these kind of structures. We've also tested this in reinforcement learning setups where we just replaced LSTMs that were used in a PPO baseline for Atari games and found that it helped on the majority of the Atari games. Okay, so we're close to the end of my presentation. Let me recap some of the hypotheses for conscious processing by agents and systematic generalization that I'm proposing we pay more attention to. So I mentioned the consciousness prior, this idea that there would be a sparse factor graph relating the joint distribution between the high-level semantic variables. I suggested that these high-level variables, for the most part, can be considered as causal variables, that they can be cause or effect of each other. And what it means really is that they are about agents, they are about intentions, and they are about objects that are controllable and their attributes. One thing I didn't talk about is that those relationships between variables, they don't have their own parameters for each factor of the graph, for each potential function. Instead, they should be shared modules that can be reused across different tuples. So the fact that we have these key value pairs, that means that a particular, say, subnetwork is going to receive input that's going to be different depending on the context. And so it's like if it's a little rule, but of course it's a neural net, that is going to be applied to different instances. So the graphical model that I'm talking about is more like a dynamic Bayes net where the same parameters can be reused in many, many places. And of course, this is also connected to Markov logic networks that Domingos proposed a long time ago. Another really important hypothesis that I spend time on is the idea that the changes in distribution are mostly localized if you represent information in the right way. This semantic space. So that's another property of that semantic space. And one thing I didn't spend much time on, but that, for example, Arjovsky and Botu have talked about in their recent paper, is that the things that are preserved across those changes in distribution have to do with the stable properties of the world. That could be, for example, grounded by an encoder, a system one aspect, that capture the stable and robust aspects of the world. So to conclude, I think after decades of work on consciousness by cognitive neuroscience, it's time that machine learning looked at these questions and explore the functionalities and the justifications for having these kinds of capabilities. And I think that this would bring new priors that could help systematic generalization and out-of-distribution generalization. It could benefit, of course, neuroscience, because we would be able to provide more detailed account of these functionalities that can then be tested in real people or animals. And it would allow to expand deep learning from system 1 to system 2. So, thank you.
Thank you very much, Yoshua, for this great talk. So please, if you have questions, come on the left side or the right side, close to the mic.
Hi. Hey. So you're talking about consciousness, and this is something I think that's really interesting. I think there's actually pretty broad consensus among moral philosophers that having conscious experience is an important part of what makes one a moral patient, in other words, like deserving of moral consideration. And then philosophers also like to talk about like the easy problem of consciousness versus the hard problem of consciousness. And I'm kind of just wondering, what your thoughts are on the moral implications of building machines that may be conscious, and if you think the way that you're talking about consciousness has any relevance to that kind of question, and also if you think that there's a way that you see for us to determine whether or not AI systems that we're building are having subjective experiences that make them relevant moral patients.
So today I've only talked about the easy problem of consciousness. There is the question of subjective experience, which I haven't talked about and deserves much more work and attention. But on the neuroscience side, people have been thinking about this for much longer. And there are some interesting theories which I think connect to issues of self-knowledge and predicting our own actions, which might explain the impression of subjective experience.
So, over here. The other major theory of consciousness is, of course, integrated information theory, which measures consciousness by this phi quantity, yes, which is essentially a measure of the mutual information of the parts of a system. And the higher the mutual information, the more consciousness you have, which seems like the polar opposite of your sparse factor graph hypothesis. How do you reconcile the two?
I don't. So I think the IIT theory is more on the mystical side of things, and attributes consciousness to any atom in the universe. And I'm more interested in the kind of consciousness that we can actually see in brains.
No, but they measure consciousness by this phi measure in brains and in computers.
There's a quantity that is being measured that I don't think is related to the kind of computational abilities that I've been talking about.
So, hi, here. Thank you for the very inspirational talk. My question is regarding the topics that you touched upon, the prior part and also the factorization part. So, in recent cognition work, it has also been shown that the human mind kind of uses the spatial world where we navigate as kind of a prior to sort our thoughts. This has been recently summarized also in a book by Barbara Tversky. If I don't know if you're familiar with that, but my question is, do you see like a role for this kind of like spatial prior, or like a way to organize certain concepts? How could we go about this?
Yeah, possibly. I think one of the big lessons of the last few decades of machine learning is we need all kinds of priors in order to encourage good solutions to the problems we're looking at. And clearly the brain is exploiting the fact that a very important aspect of the world is the spatial structure. Of course, some of our models do, but I think on the conscious side and memory side, these are also important, but I haven't looked at that. Thanks.
Thank you.
Hi, over here.
Yeah.
I'm inspired and also heartened to see that you're exploring how to integrate some aspects of, what you put, the symbolic program into deep learning and so on. I guess my question is how far you anticipate that going. There's been a lot of work, for example, on extending logic programming, which is far more powerful than just knowledge graphs or hypergraphs, to have numerical uncertainty, including scalably, computationally scalably. So that might involve interleaving fine-grain these kinds of symbolic reasoning techniques with neural network type learning and inference as it's usually conceived of in neural net or machine learning terms. So how much of that, how soon do you think there ought to be?
Well, so indeed there are a lot of people who have been exploring how we could kind of paste the symbolic logic tools on top of the neural net computation. I don't think this will work.
What I'm talking about is interleaving it
Yeah.
more tightly as opposed to just bolting it on before or after.
Yeah, but so what I'm talking about is different, and yeah, of course I don't know what will work. I don't have a crystal ball, but what I'm talking about is more implementing some of the functionalities of logic and reasoning with the neural net machinery, in the hope of keeping both properties. And one place I didn't have time to talk about where this matters is in the search. So in classical AI, a big obstacle is we have to look through a potentially exponentially large number of potential trajectories or combinations of things. And that's where system one, which is the neural net thing, comes in, right? So we learn what to attend to, what to think about, but it happens out of our consciousness. We don't know why we think about something, but that's crucial to enable efficient reasoning and search and planning and so on.
Well, thanks. We can talk more about it later.
Thanks, Yoshua, for a great talk.
Yep.
I'm curious to hear your thoughts on what is a data distribution and how we know if we're in it or out of it, and how the data distribution, what is the relationship between the data distribution and the empirical distribution? Like how, given a training set, can we exactly characterize what is the underlying distribution of that data?
Well, obviously we don't have access to the data distribution, except if we're doing machine learning experiments and we sort of cheat and synthesize the data from some handmade distribution. And so we can do it mathematically, we can do it in simulations where we know what it is, and it's very useful. But I think we also have to think about maybe how that distribution came about as a non-stationary process where things change in the world. And sometimes what looks like a distribution can be broken down into sub-distributions that are related. Think about data coming from different places or different times, for example. And we don't pay enough attention to that right now.
Hi, quick question. So you made a call to move beyond just perception to high-level reasoning and consciousness. And the question is, how do we actually measure progress towards that goal?
So I talked about out-of-distribution generalization, right? And things like transfer learning, few-shot learning, continual learning, and so on, have benchmarks, which I think is a good starting point. But in general, especially if we introduce the agent aspect, I think we have to start thinking about building environments in which we're going to test how well our learner can cope with those changes in distribution, when those changes are not like a simple set of distributions like we do right now in standard meta-learning benchmarks, for example.
Hi, I'm here. So you said these high-level semantic variables. You said in one point you said they're in a factor graph, and
yes.
then you also said they're causal.
Yes.
But usually the causal variables, we put them into DAGs.
Yes.
So can you say something on the relation?
Yeah, just put arrows on the factor graph.
And that works. Okay.
Well, I mean, so you have the joint distribution structure, and the causality is just another thing on top which provides extra information, and these are the arrows. I mean, there could be a longer answer, but that's the short answer.
Hi. Over here to the right. Hi. So, great talk. Thank you. My question is what relationship you see between sparse factor graphs and relational and associative memory supported by the hippocampus in humans, given that humans with bilateral hippocampal removal appear to be able to be conscious but not flexibly use relational associations.
That's interesting. I didn't know about it. So I don't know. I guess maybe you need that attention going back and forth between the two sides of the brain in order to coordinate the different elements of, say, a relation. So one thing maybe that has been misleading in my picture is I've drawn the conscious state as if it was something that was physically separate from the unconscious state, but in the brain that's not how it is. It's more like within the brain the unconscious part, there's some subset of neurons become excited a lot more and others become inhibited. So, and of course, that goes through a global communication. So if you break the global communication, I could imagine it would hurt the whole thing.
Thank you.
Okay, so I propose you ask your questions during the coffee break, and we are going to thank again Yoshua.